By injecting nanoscale devices into the eye, researchers at the University of Science and Technology of China and the University of Massachusetts Medical School were able to give mice the ability to detect near-infrared light, something only possible for certain animals, like snakes and insects, as well as humans using specialized equipment like night vision goggles. The eyes of mice and humans are able to detect visible light, which is a narrow sliver of the electromagnetic spectrum containing light particles, called photons, with wavelengths between 400 and 700 nanometers. Shorter or longer wavelengths, such as those in the UV and infrared ranges, are invisible. The cornea and lens filter out most UV light, whereas infrared light is too weak to activate the light-sensing cells in the back of the eye, called the photoreceptors. The researchers created upconversion nanoparticles. These are named for their ability to convert low-energy photons, like those in infrared light, into higher-energy photons, which then fall in the visible spectrum. These nanoparticles are made from rare earth metals that have unique properties. Typically, when an atom absorbs energy from a photon, its electrons become more energetic, but only for a moment before that energy is then released. For rare earth metals, that energetic state can last long enough for another photon to excite the atom and build up more energy. This allows rare earth metals to take in multiple low-energy photons and release a single photon with higher energy. The terbium and erbium are the two rare earth metals used to create the upconversion nanoparticles. The terbium absorbs the infrared light and transmits that energy to an erbium atom nearby, which can then emit green light, which we can see. Researchers attached a specific protein called concanavalin A to the nanoparticles. This ensured that when injected, the upconversion nanoparticles would stick to the photoreceptors, thereby allowing the conversion of infrared light to green light within the eye. They confirmed the nanoparticle-covered photoreceptors were able to send signals to the brain when stimulated with infrared light. While control animals showed no response, the pupils of injected mice constricted when exposed to near-infrared light. Given the choice between a dark box and one illuminated with near-infrared light, control mice showed no preference and spent equal amounts of time in both boxes. The nanoparticle mice favored the dark box, suggesting they could perceive the NIR light, and being a nocturnal animal, preferred to remain in the dark. Once it became clear the injected mice could perceive near-infrared light, researchers wanted to test if the mice could use their NIR vision to discern shapes and patterns. They did this by building a Y-shaped pool with a hidden platform. Wanting to swim to safety, mice were trained to associate a pattern, illuminated by LED visible light, with the hidden platform. When the LEDs were switched to near-infrared light, the injected mice could distinguish the pattern swimming to the safety of the platform. Control mice, on the other hand, haphazardly chose either side of the pool. These experiments were repeated, replacing the grid patterns with distinct shapes. Similar results were recorded, with injected mice correctly choosing the side with the platform, while controls swam to either side randomly. This combination of experiments showed that injecting mouse eyes with upconversion nanoparticles allowed mice to discern information about the world around them using near-infrared light. This is why humans invented night vision goggles. When visible light is negligible, ambient infrared light is converted to visible light by an external power source and then displayed on a screen. The upconversion nanoparticles could replace these bulky goggles, allowing people to see near-infrared light, thereby giving them night vision with no external accessories necessary. Unfortunately, superhuman night vision remains science fiction. These materials still need modification to become more efficient, and the FDA approval process requires a series of safety trials before commercial use in humans, which could take years. However, these nanoparticles are a very promising material, with future experiments illuminating their potential applications.